All right, let's get started. Okay, so this is what we're going to do today. I'm going to review the symmetry property that we started with in the last class. And after that, we'll talk about how to decompose a signal with its even and odd parts of the signal, and define periodic signals, how to determine if a continuous time signal or a discrete time signal is periodic. Then we go through some more definitions about instantaneous power and energy, and if we still have time, we look at exponential signal properties. Then I will return this to you. Okay? Now, here are the problems from chapter 2, for which I will post the solutions sometime next week. So you may want to work out these problems, and that way you can check your answers, procedures by next week.
Where are you going to post the solutions? Is it on Blackboard or is it?
Well, some people asked about Blackboard, so I'll post them on Blackboard.
Okay.
Okay. Yeah. So at least in
And which chapter is this for?
No, chapter 2 and all these problem 6, 8, 9.
Oh, I thought those were.
No, just chapter on from chapter. Okay. So that. Six. Okay. Oh, no, is that the number? No. What is it? Okay. Yeah. That's too far for me to reach out. Okay. All right, so we're looking at the definition of an even and an odd signal. So a signal is said to be even if the time reversed version of the signal is the same as the original signal. And in discrete time, it's the same thing. X of minus n is the same as x of plus n. As an example, we can look at, say, a discrete time case wherein there is 0, minus 1, minus 2, minus 3, plus 1, plus 2, plus 3, minus 3, and you may have, say, values like this. And this could be a value somewhere here. And so, by symmetry, you have these values. So you can see the value corresponding to minus 3 is the same as the value corresponding to plus 3. And likewise for minus 2 and plus 2, these are the same. Minus 1 and plus 1, and so on. Okay. So if you flip this signal, it's going to look exactly like the original one. And then we define an odd signal if x of minus t, the flipped version, is negative of x of t. And likewise here you have x of minus n equals minus of x of plus n. Okay, but what happens when we have a signal, let's say an arbitrary signal x of t, that when you flip it, x of minus t is not equal to x of t. That means it's not even. And also, x of minus t is not equal to minus of x of t. but it's neither odd nor even. All right. The example, of course, NLT examples are much easier to handle, but still, well, look at this. Say x of t is 3t squared minus 2t. All right. And you can verify this. All right, you take the reverse of this, that would be 3t squared plus 2t, and that's not the same as the original, and nor is it the same as minus of this. Okay. So in such cases, how do we find the components that correspond to the even part of the signal and those components that correspond to the odd part of the signal? All right. And the way we do that is based on these two definitions, odd and even part. So we go ahead and stipulate that x of t has two components. One is the even part, x of e, and the other is the odd part, x of o. And these two parts, when added together, they give you the original signal. That makes sense. So you can have any arbitrary waveform or an NLT expression for a signal, and you can split it into two parts. One part must satisfy the even property, and the other part must satisfy the odd property. Okay? So if that's the way we want to decompose the signal, then let's do the time reversal. That is, we obtain the part x of minus t. But all you have to do is wherever t appears, we replace it with minus t. And that becomes xe of minus t plus xo of minus t. Now let's call this equation number 1a actually. Yes, we're going to expand this. And then we realize this part, by definition, is the even component, even part of the signal. So if it is the even part of the signal, then we flip it, that should be the same as the original part. According to definition, yes.
What if one of the individual components is by itself neither odd nor even? Let's say.
Well, that's what we're looking at.
You can split x.
No, here it is. Let's say I'll go with single part, single component. Is it even? No. If you flip it, it's vertical, this is sloping. Is it odd? No. All right. Given this, we want to separate out its even and odd parts. All right. So we stipulate, okay, this is the original signal, which I'm saying that it's going to consist of the sum of these two components. What are those? That's what we're going to evaluate. So graphically, we can evaluate that once we know how to do that, do the decomposition.
Will there ever be something we can't separate?
Well, yeah, bear with me, just a couple of minutes, and then you'll see that. All right. So, because this is the even part, we don't have the answer yet, but we're going to get that as an even part. Xe of minus t will be the same as x of t because that's the even part. And this one, well, this is the odd part by definition, so it's going to be negative of xo of any odd part, going back to x of minus t is minus of x of t, so xo of minus t is minus of x of t. This is our equation that we want to use. As a matter of fact, I should have started with this as the as number one, but that's all right. Here. So this is the original signal with its component parts. Let's call this. And keep track of our goal. Our goal is to determine what these two are. And toward that goal, we went ahead and found the time reversed version, which are these two. Now let's go ahead and add these two. 2 plus 1b. So on the left-hand side, we have x of t plus x of minus t. All right, these two. On the right-hand side, when you add these two, the odd components cancel out, so you end up with twice xe of t. All right. Again, don't get confused because we haven't found what this xe of t is. We know this. All right, just like this one. And because we know this, when you flip it, sure, you know that as well. But this is the one we don't know. So from this, we can see that xe of t is 1/2 of the original signal plus its time reversed version. All right, simple algebra. There's nothing more to it. All right. Now tell me, what operation can you perform on these two equations so that you can get the odd component?
You do substitution now that you know what xe is.
You can do that, or
We
do
can
it simpler.
do x.
You know,
X
the
of t
hint is that
minus-
in this case we added these two.
Would it be x of t minus x of
Subtract.
negative?
So if I go ahead and take 2, from which I subtract 1b. So take 2, that's x of t, and then I want to subtract 1b, which is this is. What do we have? From this, I subtract this. So xe and xe cancel out. XO, that's negative, and I subtract that becomes positive, so I get 2 times XO of t, and therefore XO of t is 1/2 of the original version minus the time reversed. So this is the even component, this is the odd component, and clearly when you add these two, xe plus xo, half x of t, half x of t, is you x of t, half x of minus t minus half x of minus t, so they cancel out. So sum of these two, all right, is equal to the original signal, which is what we started with. Yeah.
Why are you using brackets? Does that mean we're just using discrete non-wordable brackets?
Oh no, the half goes with each term. No, we can use parentheses.
Okay.
That's no problem.
You made it clear.
Yeah, but no problem. All right. Okay, so let's first look at, let's take a simpler example here, the analytic case, and then I'll look at the graphical example. So if this is given, all right, oh, yeah, it's right here. Right. So it is an example. So example x of t is square minus 2t, and we want the even part and the odd part such that the sum of these two should be equal to the original signal. We don't want to mess up with the original signal. All right, we get the constituent parts of the original signal so that the sum would be equal to the original. We don't want to lose anything, nor do we want to add something to the original. Okay? So according to the definition, we just go over and write x of minus t. And what is x of minus t?
In this case, it's just 3.
You replace t with negative t.
Yeah.
So what do you get?
3
Plus 2t. Negative sign, and because it's negative t, so it's t. And right just underneath this, the original signal, 3t squared minus 2t. So if I add these two, x of minus t plus x of t would be 6t squared. And that, according to the derivation that we had, is twice the even part of t. Therefore, xe of t is 3t squared. which is obvious. This is the even component. But we just verified the formula we developed, that's all. Okay? And for the odd component, we go ahead and take x of t, subtract from that x of minus t. Okay? So it is x of t. From this, we want to subtract this, so what do we get? From this, you want to subtract this. So 3t squared cancel out, and then minus 4. All right? And therefore, xo, the odd component, is 1/2 of this, so minus 2. Which, again, is obvious from this. This must be the odd. Because if you flip this, you're going to get xo of minus t would be plus 2t. And that's the opposite of minus 2t. So the negative of it. If you flip this, xe of minus t is still the same. So that's the even component. All right? And you can do the same thing with the discrete time cases. Instead, I'll show you a graphical situation. I thought it would something. This. Again, the lines are not clear, so I'll have to highlight them. Yeah, I'll highlight the lines here. So here is the horizontal axis, here is the vertical axis, that you can't see. Okay, so when you view the tab, you will see something like this. All right. I tried to install something, I didn't notice it. So now it's okay. Okay. All right, so the waveform looks like this. So here is the time axis, the independent axis, and here is x of t, and it looks like this. So -3 from -3 to -1, and then it makes a jump, and then it ramps up, and then comes down. -1 and stays constant. Okay. Now, clearly you can see it's not symmetric about the vertical axis because these values are not the same. So it's not an even function, nor is it having the anti-symmetry because if you flip it, it's not going to be a negative. So it doesn't seem to possess either even or odd symmetry. So we want to get the two components such that when you add them together, the result will be this, but each individual component will have either an odd symmetry or an even symmetry. Okay? So the first step is to get the time reverse conversion. Well, when you do that, you flip it this way, so this +1 to -2, that will come in here, -1 to -2, and this range will go back to this. And that's what you see here. Okay, now we'll right on that. And if you see anything being installed, let me know so that I can change that. Okay, so that goes in. So what was on the positive side of t now comes the negative side. And what was on the negative side correspondingly goes back to the positive side. Okay. Okay, so this is x of minus t, and this is x of plus t. And so if you add point by point, remember the even component goes like this. It is the sum of the original and the time reverse version divided by 1/2. Okay, that's the definition. The original and the time reverse version, and that's what gives you the even component So in order to do that, the only difference here is that we have it in graphical form. Bend over. Okay. So for instance, let's say we want to get approximately over the range x e of t, which is the sum divided by 2. And let's work in this range. Say at this instant, let's say we are going from -2 to -1.9. So we are proceeding in the positive time axis. Okay. So at this time instant, what would be the value that gives you the sum divided by 2? Well, this is giving you -1. This is giving you -3. So sum of these two, -4 divided by 2, -2. So that's what you get at this instant. And then this is constant, -3. This is constant, -1. So sum of these two, -4 divided by 2. And how long does it continue? Tell me the time instant. It starts at -2. That's the time instant. Does it go all the way to 0 or +1 or
-1.
up to -1? Because this stops at -1. All right. These are not aligned, are they?
No, they're parallel.
Wait.
Should we start at -3?
-3, yes.
Yeah, that's
Okay.
right.
So yeah, good. So up to this point, yeah, say 91. This point is okay. All right. So this is the one we need to revise. Okay. What about at -3, which is in here? No. No, it looks like -3. Okay. At every instant, remember this is a variable, at every instant you add these two and divide by 2. So this is contributing -3, this is contributing nothing. Sum of these two divided by 2 minus 1.5. So you get -1.5, less than -2 here, and continue from -3 to -2. And then this comes into play, so sum of these two goes to -2. All right? And after that, what happens after that? Let's pick one time instant. This is +3. This is +1. So sum of these two, that's 4. 4 divided by 2, that's 2 in here. Okay? So it makes a jump. To 2.
And that goes +1.
And then, if you look at this instant, this is +2, this is also +2. Again, it continues on. Shall we go all the way to +1? Yes, because 3 + 1, 4 divided by 2. 2 + 2 divided by 2. 1 + 3 divided by 2. So it goes. Now, we can continue this way. All right, I'm looking at time instant 1. This is -3. This is -1. Therefore, -4 divided by 2, -2, and so on. Or, I'm confident that from -3 to 0, this is correct.
And it's even. So.
Because it's the even component, I can just flip it back. All right? Because it's the even part, it has to be the same, whether it's for positive t or negative t, so I can simply flip it back. Well, initially I'm not so sure, so we can go ahead and calculate at each and every point, and then we can verify that it is indeed going to be like this. Because it has to be even, that is the even. Okay? For the odd part there, I want you to complete that, and you have the answer in the book, you can look it up. So for the odd part, likewise, say if I start from this instant, this is 0, this is -3, so 0 minus of -3, positive 3 divided by 2. And then that situation continues from 3 down to 2. All right. And after this value kicks in, so you have to take these two. Okay. So that's how you determine for a graphically defined function x of t, and the definition, of course, doesn't change. Whether you do it graphically or analytically, it's still the same. All right. Any questions? Okay. All right. So with that, let's move on to. I do have a final answer for the even part of this. But anyway, you have it. So the next item is about periodic signals. So start with the continuous time case. Okay. Let's say x of t, general signal. Okay. It is said to be periodic in the independent variable time t if x of t plus t, some constant. Notice we use uppercase for constants, lowercase for variables. Right? If x of t plus t equals x of t for all time instants t and smallest positive big T greater than 0. 0 would be trivial case. All right. So let's look at some examples that are periodic and that are not periodic, both cases. Okay. All right. So I will go ahead maybe something like this. And it goes further. It has to last forever, negative infinity to positive infinity. So this is x of t. A sawtooth or a ramp waveform. Okay. So again, I don't need to put the time origin because it replicates itself after certain interval. The time origin could be, for instance, or it could be anywhere. It doesn't matter. Okay. So if I start off this way and I find, well, this value is 0, is repeating here. This amplitude here is repeating here. This amplitude is repeating here. This amplitude is repeating here. And then I go to the 0, then I go back to this one and so on. All right. So then I can see, well, this looks like the smallest time period t after which it repeats itself. All right. What if I start here? Well, once I have determined this big T, start here, go by big T amount, I end up here, which is the same. And then if I start here, go up big T, I end up with the same value, likewise here. So that's periodic. And it doesn't have to have such nice shape either. Anytime you do the rectification to build a very inexpensive power supply, you end up with a half-wave rectified sinusoid, which you would have seen in 275 if you have already taken that class. Even otherwise, it doesn't matter. I'll just show you what it is. And it continues. In other words, the bottom half of the sine wave is removed. It is no longer there. Okay? So it goes both sides. What's the period? You start here. This value is the same, but wait, if you go here, that's not the same. So then you'll have to go. So that way, these are the same, these are the same, these are the same. So your period is then T. All right? And this little t, that can be anywhere. I can, maybe I arbitrarily start here, and then I go big T time instant later, I have the exact same value. So this interval is big T. Right? So this is another periodic signal. Right? What if I have, let's say, it looks like, maybe it's an exponential decay. It's a one-shot wave. I have a charged capacitor and I discharge it via a resistor so that I have a time constant, and so it decays exponentially, e to the minus 2t or something like that. In theory, of course, it will come to zero only when t goes to infinity, but in practice, after 5 time constants or so later, it's only 5% of the maximum. So this is 1, this is not extremely small. Regardless, this is a one-shot waveform. It doesn't reproduce itself. That's not a periodic signal, right? Non-periodic or aperiodic. Okay, so this is good. If you're given graphically, visually you can determine if it's periodic or not. All right. Do these amplitudes reproduce themselves after a small amount of time, the smallest possible time? Because the same value is also here, is also here. You don't consider this to be t because that's not the smallest value. It's this one. All right. So that's how you can determine based on graphical representation. Right? Analytically, then, how would you do that? Let's say I have x of t is x 3 sine 100 pi t. All right. Now, let's leave it at that, then I'll throw in a phase angle. Right? So the question is it periodic? If so, what is its period? All right. So what is T? If you claim it's periodic, we should know what its period is. Okay? So we'll proceed with the assumption that it is periodic, and then try to evaluate this T. If it's positive with a value other than 0, then indeed it's periodic. If you cannot find any T, then it's not. Okay? So proceed. Let period be t. Then according to this definition, we go with x of t plus t equals 3 sine 100 pi t plus t. Okay. And this must be equal to x of t, which is 3 sine 100 pi t. All I'm doing is simply following this definition. So far, nothing new. All right, that's the original signal, and I'm replacing this little t with little t plus big T. All right. So I'm going to write down these two terms here. So I have 3 sine 100 pi t plus 100 pi big T. I expanded the quantity inside the outer parentheses, and that must be equal to 3 sine 100. Okay. Shall we cancel this 3? Is that on both sides? All right. Divide it out. Okay. So then, sine of 100 pi t plus something must be equal to sine of 100 pi t. Right? So this is where I ask you to remember certain basic trig functions. All right. We know sine is a periodic function. All right. But besides that, we need to know what values of the argument will make the sign to periodically repeat itself. So that's where I want you to know these basic sine and cosine properties. Sine of alpha plus 2L pi, where L is an integer. It can be 0, plus 1 or minus 1, plus 2 or minus 2, and so on. As long as it's an integer, not a fraction. Okay. That simply sine of alpha. Right? That's an extremely important property, and we'll come across this over and over again. Right? So whatever mnemonic, whatever technique you can use that to remember this. Okay? All right, let's look at one way of remembering this. Let's go with a circle of radius 1. So it's minus 1. You can even go in the complex plane. So this is real, imaginary, plus j1 minus j1. Or simply leave it as 1 for now. Doesn't matter. Okay? And I pick a point here. This is the origin. I pick a point here, okay, which is at an angle alpha. So what is sine of alpha? Let's call this A. What is sine of alpha? Well, from this diagram, don't go back here. Sine of alpha. Which one?
Sine of alpha plus 2 pi.
No. Just looking at this right triangle, tell me what's sine of alpha.
B over there.
B over the hypotenuse, which is 1. All right? That's B over. And again, it doesn't have to be 1. I just chose this so that the ratio would be simply equal to. But if it's something else, then you would have to go with the radius. So the opposite side, that's B. All right? The distance from the origin to this point along the vertical axis, and then the hypotenuse, whatever value. If you call this radius R, then it's B over. Right? Now, I take this alpha and I add 360 degrees. Where will I end up? Same place. That's all I want you to remember. All right. If I have this and I'm starting here and I'm adding, let's say for argument's sake, this is 30 degrees, and I'm adding 60 degrees, that'll bring me here. Another 90 degrees, that'll bring me back here. One more 90 degrees, bring me back here. One more, and here. And then I got to go back so that I can complete one whole round. And one whole round, that simply means adding 360 degrees. Right? Or, in terms of radians, 2 pi radians. So we go around one whole cycle or interval or angle. That means we are adding 360 degrees of 2 pi radians, which brings you to the exact same location. So after adding, that is alpha plus 360 degrees or alpha plus 2 pi radians, I am where I started out. So sine of this is still going to be the previous sine value. All right? Sine this is sine alpha. How about if I go in the clockwise direction? Subtract. Again, if I subtract 360 degrees, I come back here. That's why it's plus or minus. 720 degrees. 2 cycles. 2 rounds. Still the same thing. So that's why it's an important property here. And the same thing. If I go with cosine, I go with cosine. The sine and cosine is still the same. Okay? That's the property we want to use here. Okay, so when you come to this, I want these two to be equal. You can think of this to be your alpha. So we're talking about sine of alpha plus 100 pi t, big T, equals sine of alpha. The only reason I put alpha is because I don't want to carry through all these 1, 2, 3, 4, 5 characters, especially if I'm typing, word type 5 characters, if I can do away with only one number. Okay. And what does this imply? What would make this equality true? Look at this property. This implies this 100 pi t. All right. If it is 0, sure enough, sine of alpha, no problem. But that's trivial. All right. Both sides are exactly the same. 100 pi t can be 2 pi. It can be positive or negative. It can be 4 pi, again positive, negative. It can be 6 pi, positive, negative, and so on. All right? Full circle brings it back to you. Okay? Well, all are equally valid, but we want the smallest positive, smallest and also positive, so that you choose 100 pi t equals positive, so it's only plus, and then smallest, that's 2, which tells you t has to be pi and pi cancel out, 2 over 100 seconds or 1 over 50 seconds. So if you sketch this waveform, it's a sine wave. That's just for our own interest. It doesn't have to be sketched. Once you find this t, and that's greater than 0, therefore it's periodic. To complete the answer, it's periodic with a period t equals 1 over 50 seconds. Right. Now, if you sketch, look on that. And continues. And remember one thing, any periodic signal has to exist for all time instants. So you cannot stop after this. All you can do is, put these ellipses so that you understand it's stretched on both sides. So this is t versus x of t. And what's the peak value here? It's 3. It's 3 here. And this one? Negative 3. Okay. And so if you look at the period, you can go from here. Is that a period? No. You're going to go in here. And that's 1 over 50 seconds. Okay. Or you can go from peak to peak, 1 over 50 seconds. Or you can go from this point to this point, again 1 over 50 seconds, and so on. Okay, here is a question for you. And before I ask you the question, I give you one opportunity to clarify if any questions. Any questions about this? Nothing? Okay. All right. What would be the period if I have, say, some other function? G of t is 3 sine 100 by t minus 30. Is that periodic? Yeah, by looking at sine, you can guess. All right. But when you try to evaluate the big T in the period, what would that be?
It would still be 1 over 50. Minus the 30 degrees is just
It would
check.
still be 1 over 50. All right. One way to look at it is this. Oh, this is 30 degrees. That's phase lag. So at the time t equal to 0, you have a value 3 sine minus 30 degrees. So minus 30 degrees, that's somewhere. So all it says is your vertical axis has been shifted to this point. It did not do anything to alter the waveform per se. It's still intact. The time where you observe is now changed because of this phase lag. Other than that, the shape is preserved, no change whatsoever. Okay? Well, that's what you're saying. How do I know? Okay? Or how do I know the speed is? Just follow through. Exact same steps. I want you to complete that to get a better understanding of this. So you would say g of t plus t is 3 sine 100 pi t plus t, and everything else is intact. Only that little t has been changed, which in the step I can write as 3 sine 100 pi t minus 30 degrees plus 100 pi t. And that must be equal to 3 sine 100 pi t minus 30 degrees. So these two should be equal if it is periodic. And you can call this to be your alpha. So you have alpha here. So it ends up being 3 sine alpha equals 3 sine alpha plus 100 pi t, which is exactly what we have here. And 3 and 3, then, of course, they're cancelled out. So it's the same. This minus 30 degrees, that kind of tags along, whether you have it in the original signal or in the time shifted signal, it's still the same. So it doesn't do anything to change the waveform. So you might as well group it with this and call it as alpha. All right. So these two, the equality here is exactly the same as the equality here. So you end up with the same time period. Yes. Okay. All right. Now this is very good. But when you go to discrete time, it doesn't work for sines and cosines as the way we are seeing here. All right. So one example that's non-periodic without having to sketch. So here's x of t is phi e to the minus 2. And it is defined for t greater than or equal to 0 or even for all t. After all, a periodic signal must exist for all t, so might as well define it for all t. Is this periodic? Well, yeah, I mean, once you sketch, you know it's not. But if I want to do it analytically, I will have to say, let x of t be periodic with period t, with, I should say, period t. Then x of t plus t must be equal to x of t, which indicates phi e to the minus 2 t plus t equals phi e to the minus 2. And I can cancel out the phi on both sides. E to the minus 2t, e to the minus 2 big T equals e to the minus 2. Which implies, if I divide out by this term, I end up with e to the minus 2t equals. So far, nothing wrong, all right? So what is the value for t such that this equality will hold? 0. 0 is the only value for which this will be true. All right? So after how much time does it repeat itself? After 0 time. All right. So because it is 0, x of t is non-periodic. Because we must have a time instant that's positive and the smallest value. Well, this is the only value positive, so it's not periodic. Okay. So for discrete time case. Again, the same definition, x of n must be equal to x of n plus n for smallest n greater than 0. It must be positive, and it must be the smallest possible value. Okay. And keep in mind that this n is an integer variable, cannot assume any fractional value, all right? And this big N is a constant, integer constant. Okay. To illustrate this, let's look at, since started with the triangular overload. So if I go, let's say, and so on. And let me throw in the values for n. Maybe I'll start here. This is n equal to 0, 1, 2, 3, 4, 5, let's say 8, 10. This is negative 1, negative 2, negative 3, 4, 3, negative 5, and so on. All right. So does it look like it's repeating itself? Yes. Right. After how many samples?
5.
Is it 5 or 4? 5. All right. Let's say if I start here, I have this value. The next one, no, it's not equal to this. Next one is not equal to this. Next one, next one. And so 1, 2, 3, 4, 5. After 5 samples of 5 values, I have this repeat. And if I start, for instance, here, all right, 1, 2, 3, 4, then I end up with this. All right, it is repeating itself. So this has a period of n equals 4. And likewise, for any graphically defined function, by observation, you can determine. Now let's look at the analytic case where the difference arises between the continuous and the discrete time situation. So here is x of n. It's sine, let's say, 0.2n. Now, just because it's sine, you shouldn't be thinking, oh, it's automatically periodic. I don't know what the period is, but I can tell you it's periodic. Well, no. All right, and that's what we want to find out by using this definition. Okay. So let's start with this. Let the period be n. And according to the definition, then x of n plus big N must be equal to x of. Everything is discrete. Okay? So now let's replace this with sine of 0.2n plus big N. That must be equal to sine of 0.2. Okay? So you expand this as 0.2n plus 0.2 big N equals sine of 0.2. If you want, you can treat this as some alpha. This is the same alpha. So you're looking at sine of alpha plus 0.2n equal to sine of That's an equality. And in order for this equality to be satisfied, what's the condition? Going back all the way here, looking at this property, if these two have to be the same, then the second quantity must be an integer multiple of 2 pi. Integer multiple, where L is an integer, it's an integer multiple of 2 pi. So this implies 0.2n must be equal to 2 pi times L, where L is 0 plus minus 1 plus minus 2, etc. Integer multiple of 2 pi. Right? That would imply, therefore, n equals 2 pi L over 2. And you're going to choose the smallest positive value. So what would that be? If we put n equal to 0, then n is 0, that's trivial case. All right? It repeats after every 0 seconds, that means it's not periodic. Okay? I can't use negative because I need to have this as positive. So if I go out with 1, well, that will be 2 pi divided by 0.2. All right? That will be 10 pi. But that looks like the smallest value. What's wrong with that? Go ahead. It's not an integer. That's the key here. Smallest n greater than 0, and that has to be an integer constant. All right. You remember when we sketched it, we did not sketch it. Oh, for 3.2, that's the same value. 3.5, that's the value. No, we said there is a sample at 3, and the next one is at 4. Nothing in between. No fractional values for it. N has to take on only integer values. So this is not an integer. Right, not an integer, but I already put the inequality. Okay. So no matter what L you choose, or you want an integer value, I can choose, say, L equals 25. Still, it's not an integer. Okay. Therefore, it's a periodic. It's not periodic. But if you go to MATLAB, and it's very easy to use it in MATLAB, you can define, for instance, n is, let's say you go from minus 100 in steps of 1 to plus 100, or linear space, whatever you want to use, and then you want to say x equals sine of 0.2 times n, and then you plot this. It will look somewhat like this. All right, just two statements, nothing else. And after that, you plot x, or x versus n, either way. Okay? It will look like this. I'll just trace the outline, and it won't be exactly on the outline, but just for illustration, I'll do that again. So it'll look like. So at the outset, it may appear to be periodic, but you will not find any n, any number of samples after which it exactly reproduces. It will approximately be in this shape, but not really periodic, obviously.
So does that mean it's like impossible to make a truly periodic digital?
I'll go into that, yeah. The next example, yeah. All right, yeah, next example. So if I make a small change to this one, but let's compare that. So go to this. X of n is maybe 4 sine 0.2 pi n. That will be periodic. Why? Let's look at the definition. So we are looking for this value of n, which would satisfy this equation. And so you have 4 sine 0.2 pi n, this big N, equals 4 sine 0.2 point. And then 4 and 4 cancel out, divide it out. And so we end up with sine of 0.2 end point plus 0.2 big end point is sine of 0.2 end point. So now you can call this your alpha. Yeah, whatever. This is your alpha plus 0.2 end point is sine alpha. Okay? And in order for this to be true, this term 0.2 end point must be equal to 2 end point, where n is 0, plus minus 1, plus minus 2, and so on. Okay? So then n becomes your pi and pi cancel out your 2l over 0.2, and that would be 10 n. We need to choose the smallest integer. We don't want to choose L equal to 0, that will give me period of 0, which is not periodic. We can't choose -1, that will give me negative value. We cannot choose 2 or 3, that won't be the smallest value. So then choose L equals 1, that gives 10. So after every 10 samples, it repeats itself. Right? Now, I want to try the, wish I had a different color, but let's go with 3. So I'm going to change this to 0.3, and then pi, everything is the same, all right? 4 sine 0.3 and pi instead of 0.2, and tell me what the period is. Okay? And I'm not saying that's a hint for your next quiz, but if I did, forget that. All right. Any question about this before I return your quiz? Yes.
Does it matter if continuous time is L or discrete time is used for K?
Oh, that is, I mean, this L, that's an integer, that's all. It's an integer. For a continuous and discrete, this property is always valid. This is always true. L has to be an integer. If you want to use K, that's okay. It just assumes this value. Okay? All right, so before I return to quiz, I want to make some observations. And the key observation is that some of you didn't get anything, who got below 5. Okay? You really need to review your calculus. Second one is try to use the simplest possible approach before you get into more elaborate techniques. Okay? So, hard time decoding your name, so don't get the name correctly. Sean Jen. John Rodriguez. Next, you will have Obrigado.
Put it there and we'll grab it.
This is Miles Weber. Weber. Joseph. Jeff Trumbull. Ryan Henry, right?
If you want to see a time, you could just go there and go around.
Robert McKenna. Yeah, let's save some time.
Fair enough.
I'll definitely save time. Richard, what else? Melanie, Jenny, Rosario. Okay, this one and this one. Gilbert. Victoria. Alex, Sean, what's Vasco, Andres, Correct. Muhammad Al-Hussein. Karen Grace. Brandon Elliott. Daniel Springer. Ogden James. Alexander. Kevin. Jones. Abel Grace. Ahmed Farid. David Ahmed.
Let me see Eric.
Adam, Adam. time we have to find some other way to cut down. People may not want to look at this. Mike, that's good. Muhammad, Daniel, Jack McShane, James Ellenberg,
I thought you said
Austin Henson, Naftali Abdul, Johnny Perez, Jordan Osborne, Jesse. All right. Just once. If you did not put this 100 pi, that's a grave error. Okay, you need to be able to integrate cosines and sines. All right, and some people put it as 100 pi times, which is incorrect. And some people didn't put this at all. All right, and the last item is that 0.02 times 100 pi, that's 2 pi, and sine 2 pi, that's 0. So you got to show the steps. And this being the first one, sometimes I may have ignored it, but in future you got to show steps. You can't simply say, oh, that's a cosine function, so I'm getting it to 0. Okay? What if I have a different range? Say I go from 0 to 0.01 instead of 0.02. So you have to write down this. And same thing goes here. Okay? Several of you, at least 5, 6, I guess, for instance, you split this range -1 to 4 by looking at this graph. -1 to 4, you go from -1 to 0 because in that range it's a fixed function. And then 0 to 2, again a constant, a fixed function. 2 to 3, one more function. 3 to 4, it is 0. So you show this interval in between and evaluate for each interval. Here, I think I mentioned in the first class about not having to write down the expression, particularly if these are simple functions, and yet at least 3-4 of you went with expressing this and this in analytic form. Nothing is wrong, okay? It's perfectly all right, but it's the same situation. If I ask you to touch your nose, you can do it this way, or you can go all around and do that, and say, and claim, not say, oh, I can't do that. It's too far away. All right? That's exactly what happened. It's a straight line, so people took it as, oh, it's 3t, or it's minus 3t. Neither one is correct. And it takes more effort trying to come up with an equation for these, for each of these straight lines, than to find the area below the graph. You can find the area from -1 to 0 directly from, you mess it up here, like this. Or you can say, well, I will find this area, the whole triangle, and then I'll knock off this triangle. Either way, it's fine. Rather than trying to write an expression for this line, and same thing for this line. Okay? Going further, this is a rectangle. I think most of you got that. 2 times 3 as a right triangle. Again, this is the right triangle. So that's what you got to pay attention to. Okay. My goal is for you to understand and do the problem, not to torture you with going through, all kinds of steps. It doesn't do anything because we build up on concepts. All right. So be aware that the secret is out. You will have a quiz Thursday. All right. It could be from the symmetry property that we went over today, or it could be from the periodic signals. All right, how to find the period if it's periodic, or if it's not periodic, then you have to show the proof. You can't simply say, "Oh, it's not periodic," based on what. So now onwards, you have to include the steps, and that way, even if you go wrong somewhere in between or toward the very end, at least I can look at the intermediate steps and give you partial credit. I wrote in many of the sheets, but I want to make sure that everyone understands that. Show the steps, even if it's a trivial case, show the steps. Okay? That way, I can check off whichever steps you went through correctly and give you partial credit. Okay? All right, so that's it for now. So we'll see you.